Hi everyone, my name is Zhenjian. I'm going to talk about an efficient coding theorem via probabilistic representations and its applications. This is joint work with Igor Oliveira. Let me first give an overview of our work. We are interested in the following question related to data compression. Can we show that objects that can be efficiently sampled also emit short and effective representations? Here, short means we can compress the objects into few bits, and effective means given this compression, we can decompress and recover the object relatively efficiently. A classical result in chromograph complexity called the coding theorem says that if an object can be sampled with probability delta, then it has a representation of length about log 1 over delta. In this work, we prove a time-bounded version of the coding theorem, which shows that efficiently sampleable objects emit short and effective probabilistic representations. Let me start with a quick introduction of chromograph complexity. So chromograph complexity is a complex measure of individual binary strings. And we can think of it as a measure of the amount of randomness of a string. And the chromograph complexity of a string x, denoted as k of x, is defined as the minimum length of a Turing machine that prints x. For example, if x is the string that has n zeros, then to print this string, we can use the Turing machine that prints 0 n times. And to describe this machine, we need to specify the number n, and this can be done using log n bits. Then the size of this Turing machine is log n plus some constant. So the chromograph complexity is of x, in this case, is at most log n plus O of 1. And on the other hand, if x is some random looking string that does not have any specific pattern, then we may not be able to find any Turing machine that is much better than the one that prints each bit of x one by one. And in this case, we need to specify the whole string for such a Turing machine. So its size is n plus some constant. So we can only say that the chromograph complexity of x is n plus O of 1. From the definition, we know that a string has small chromograph complexity indicates that it has a short representation, which is given by a small size machine that outputs it. But this does not tell us how long the machine needs to run to output the string. It would be more useful if we can say that the string has a short representation, and given this representation, we can recover the string in a relatively efficient way. In the 1980s, Levin proposed a version of time-bounded chromograph complexity that takes into account the running time of the machine that outputs the string. It is called a KT complexity and is defined as follows. From the string x, we again consider all the machines that outputs x. And for each such machine, we look at the sum of its size and the log of its running time, and we take the minimum of this sum over all these two machines. So with this definition, if the KT complexity of x is at most k, then we know that x has a representation or it can be compressed into at most k bits. And given this representation, we can recover x in time 2 to the k. Recently, Oliveira proposed a randomized analogous of Levin's KT complexity. It is called RKT complexity and is defined in a way that is similar to KT complexity. The difference here is that instead of considering deterministic machines that outputs x, this RKT complexity considers randomized machines that outputs x with high probability, like with probability at least 2/3. So for RKT complexity, we take the minimum sum of the size of a randomized machine that outputs x with high probability, plus the log of its running time. Therefore, a string x has small RKT complexity means that x has a short representation, and given this representation, we can probabilistically recover x with high probability. There are three fundamental results in chromograph complexity: the language compression theorem, symmetry of information, and the source coding theorem. And we will not get into the details of the first two, and we will focus on the source coding theorem in this work. But before talking about the source coding theorem, let me say that the question that we are interested in is whether we can translate these three results for chromograph complexity to the time-bounded setting, which may be more useful in the setting of complexity. And unfortunately, it was observed that under some Harless assumptions, language compression and symmetry of information do not have a time-bounded version. And on the other hand, we do not know such negative evidence for proving a source coding theorem in the time-bounded setting. Let's now look at the source coding theorem for chromograph complexity. Essentially, it says that for a string X, if there's a computable probabilistic distribution D such that the probability of X with respect to the distribution is at least delta, then the chromograph complexity of X is at most log 1 over delta plus some constant. As mentioned earlier, we are interested in establishing a time-bounded version of this theorem. For example, if there's an efficient sampleable distribution that generates a string X with probability at least delta, can we show that the time-bounded chromograph complexity of X is at most about log 1 over delta? In fact, Antunes and Fortlau implicitly prove such a coding theorem for KT with very good parameters, but it requires a strong de-randomization assumption. In this work, we've shown an unconditional source coding theorem in the time-bounded setting for RKT. More specifically, we show that suppose we have a randomized algorithm A that takes some input 1 to the n, and it runs in time t of n and outputs a string X with probability at least delta. Then we can say that the RKT complexity of X is at most O of log 1 over delta plus log t plus log n. And the important thing here is that the RKT complexity in this case is close to log 1 over delta. However, we'll only get O of log 1 over delta instead of log 1 over delta as in the original coding theorem. And it is an interesting open question to improve this log 1 over delta to be just log 1 over delta. Another interesting feature of our coding theorem is that given such a sampler, we can generate an RKT representation efficiently. More precisely, given the string X, the sampler A, and the numbers m and delta, with high probability, we can compute in time polynomial in the length of X, an RKT representation of X with complexity at most O of log 1 over delta plus log t plus log n. And here, an RKT representation of X with complexity at most K means a randomized Turing machine that prints X with high probability, such that the size of the machine plus the log of its running time is at most K. The key here is that the running time of this procedure is polynomial in the length of X, and it does not depend on the running time of the sampler. And using this feature, we further show that there's an instant-based search to decision reductions for RKT, which I will explain next. A decision problem asks whether a solution exists, while the search problem asks to output a solution. And a search to decision reduction is a procedure that solves the search version of the problem efficiently using an oracle that solves the decision version. And we say that a search to decision reduction is instant-based if it only queries the oracle on the instant that we want to solve for the search problem. So in other words, if we try to solve the search problem for X, then we will only use the oracle to answer questions about X. We consider the following decision problem of RKT. So given a string X and a number K, we are asked whether the RKT complexity of X is at most K. And for the search problem, given a string X and a number K, we need to output an RKT representation of X with complexity at most K, if the RKT complexity of X is at most K. And we also need to be able to tell if no such representation exists. Again, an RKT representation of X with complexity K means a randomized machines that prints X with high probability, such that the size of the machine plus log of its running time is at most k. Actually, here we will consider the approximate version of this problem, where we are asked to output an RKT representation of complexity at most O of k rather than k. Our result is a randomized instant-based search-to-decision reduction for RKT, which says that given a string X and a number k that is at least the RKT complexity of X, we can compute in polynomial time with high probability an RKT representation of X with complexity at most O of k. And also, we show that such reductions exist for KT complexity. For the rest of this talk, I will talk about the proof ideas of our source coding theorem for RKT. Let's first try to do something that is very simple but captures the basic idea of the proof. So suppose we have a sampler A that runs in time t and outputs a string X with probability at least delta. We want to show that the RKT complexity of X is small. And it suffices to come up with a fast algorithm that outputs X with high probability using some short string. So let's denote it by alpha. Now let's assume that alpha is exactly the string X that we want to output. And of course, this assumption does not make sense, because in this case, we can simply output alpha. And we will show later how to remove or weaken this assumption. But for now, suppose we have this string alpha, which is the string X. Then we can try to output X by doing the following. We run the sampler A O of 1 over delta times. And each time we compare the output of the sampler with the string alpha. If they are equal, we just return the output. Because the sampler A outputs X with probability at least delta, and we run A for O of 1 over delta times. So with high probability, one of the outputs of A is X, and in this case, we will correct T outputs X. Now we need to get rid of the assumptions that the string alpha is X. The idea is to use hash functions, and we will use the hash value of X instead of X itself. Let's first talk about hash functions, or more precisely, hash families. A hash family is just a collection of hash functions that maps n bits to some L bits. So each hash function maps n bit strings to 2 to the L buckets. And one property that we want our hash function to have is that they can map a small set of elements to different buckets. And let's say that a hash family H is useful for subsets of size k if for every subset W of size at most k. If we randomly pick a hash function from H, then with probability at least 0.99, the hash function that we pick maps the string in W into different buckets. Another way of saying this is that for every distinct pair X and Y from the set W, their hash values on these hash functions are different. And in this case, we also say that the hash function isolates the elements in W. And suppose we want to have a hash family that is useful for subsets of some size k. The question here is, how large do the hash family and L needs to be in order for it to be useful? And there are long results in the literature which says that there exists a hash family H that is useful for sets of size k, where the number of hash functions in the family is polynomial in n times k, and the output length L of the hash functions is O of log k. And in fact, each hash function in the family can be encoded using O of log n times k bits, meaning that given such an encoding, we can obtain in poly n time a circuit that computes the hash function. Let's now get back to the proof of the coding theorem. Again, we have a sampler A that outputs X with probability at least delta. And we want to design an algorithm that outputs X with high probability using some short string. And let's denote by n the length of the string X. And let W be the set of n-bit strings that are generated by the sampler A with probability at least delta over 32. Note that since each string in W has probability mass at least delta over 32, the size of W is at most 32 over delta. And let H be a good hash function that isolates the string in the set W. And we can select H from a hash family that's useful for W. And we know that most hash functions from such a family will be good. And from what we know about the size of the set W, we can have a good hash function whose output length is O of log 1 over delta bits. And it can be encoded using, say, O of log n over delta bits. And finally, let alpha be the hash value of X using H. And note that the length of alpha is O of log 1 over delta. Let me now describe an algorithm that outputs X with high probability. We first run the sampler A t times, where t is something like 64 times 1 over delta times log 1 over delta. And we get a set of strings, which are the outputs of A. So let's call this set V. And V is a multi-set that can have multiple copies of a string. And next, we will remove from the set V the strings that appear less than some threshold, say less than 32 times log 1 over delta times. Let's make a couple of observations here. Since A outputs X with probability at least delta, if we run A t times by our choice of t, the number of appearances of X in the set V should be above the threshold with high probability. And this can be shown using standard concentration bound. And on the other hand, if a string is locked in the set W, then the probability that A outputs it is small, like less than delta over 32. So it is unlikely that such a string appears too many times in the set V. Again, using standard concentration bound, we can show that after removing the strings whose number of appearances are below the threshold, we are only left with strings that are in W. Therefore, after this second step, with high probability, the set of remaining strings contains X, and it only contains string in W. And also, since our hash function isolates the strings in W, so given that this remaining set only contains strings in W, we can conclude that there is only one string in it whose hash value is the same as the hash value of X, which is X itself. And for the rest, we will apply the hash function to each string in this remaining set and check if the hash value is equal to alpha, which is the hash value of X. If yes, then we return the string. And this is the whole algorithm. Finally, note that the algorithm lists the following information: the code of the sampler A, the encoding of a good hash function, the hash value of X, and the number n and delta. And this information can be encoded using O of log n over delta bits in total. And also, it's easy to check that the running time of the algorithm is polynomial in t over delta, where t is the running time of the sampler. And as a result, we can conclude that the RKT complexity of X is at most O of log 1 over delta plus log t. And this completes the proof of the coding theorem for RKT. And that's all for this talk. Thank you for watching.